then we looked at the definitions of the energy of a signal and the power of a signal. I would like to just do a few examples so that you are comfortable with the application of the concept of energy and power. Okay. So, the first one that we would like to do is, we are given, so these are examples, we are given that the energy of x is equal to summation n equal to minus infinity to infinity x of n magnitude squared. Okay, this is some finite value which is given by E of x. Now, obtain the energy of x1 of n, which will be denoted by E of x1, which is where, okay, let me do it like this. Obtain the energy, I am going to write it here as E of x1, where x1 is equal to x1 of n equal to x of minus n. Okay, it is a time reversed version. I am sure you can argue saying, okay, when I go from minus infinity to infinity, whether I do the energy calculation from minus infinity to infinity or from infinity to minus infinity, it does not matter, it is going to be the same. Okay, but I would like you to also be comfortable showing this mathematically. So, the energy Ex1 is given by summation n equal to minus infinity to infinity x1 of n magnitude squared, that is the definition. Okay. Now, substitute for x1 of n, this is n equal to minus infinity to infinity mod x of minus n magnitude squared. Okay. You have to do a change of variable, let m equal to minus n. Then the summation again will go from minus infinity to infinity, m equal to minus infinity to infinity. Now, what you will have is modulus of x of m magnitude squared, which is the same as Ex. So, in other words, Ex1 is the same as Ex. Of course, this is something that we knew, but you should just the formality of writing it down in the following expression. Okay. Now, for this signal, if what is P of x? If I ask you to calculate P of x, if the energy is finite, then P of x will be equal to 0. Right, that's any finite energy signal, any energy signal, the corresponding power expression will be 0. Okay, let us look at one more example, again useful for us to write down these expressions. Okay, so this is another example. We are asked to compute Px and Tx. Compute Px and Ex. Energy and power. Okay, we are asked to do it for, we will just do two simple examples. X1 of n, this is the first problem, is equal to 1/2 power n u of n. Okay, expression for E of x will be n going from minus infinity to infinity mod x1 of n magnitude squared, but x1 of n starts only at n equal to 0. So, this summation becomes n equal to 0 through infinity. I have half power n, when I square it, it becomes half power 2n. Okay, this is the same as saying summation n equal to 0 to infinity. I can take 1/2 squared, which will be 1 raised to the power 1 by 4 raised to the power n. Again, this is just simple. And then I have a geometric series. This will be 1 over 1 minus 1 by 4, which is the same as 4 by 3. So, we have verified for this particular sequence E of x1 is equal to 4 by 3. The minute you get E of x to be finite, P of x1 without hesitation you can say is 0. Okay. Second example, x2 of n is equal to e power j pi by 2n plus pi by 8. Okay. It is a complex exponential, e power j pi by 2n, and e power j pi by 8 is a scale factor. You can treat it as a complex scale factor. Now, what is mod x2 of n? Mod x2 of n is modulus e power j pi by 2n plus pi by 8. E power j theta is a unit vector along the theta direction. So, if I take the magnitude, this will be equal to 1. So, the energy of x2 will be summation n equal to minus infinity to infinity mod x2 of n magnitude squared, okay, and this is going to be equal to infinity, because I am adding infinite number of terms which are all equal to 1. Now, P of x2, remember we said you take the summation from n equal to minus k to k, divide by 1 by 2k plus 1, and this will be mod x2 of n magnitude squared. So, this will come out to be, you are adding 2k plus 1 times in the of the number 1, and the scale factor of 2k plus 1 in the denominator, this is equal to 1. So, for these complex exponentials, you will get, these are sinusoid which are periodic functions, energy will be equal to infinity. The power you have to calculate, but in this case we calculated, comes out to be equal to 1 in this particular example. Okay. And last one, this is more to just to help you work with the trigonometric identities. So, a third one where you also asked to calculate the energy and power. x3 of n is equal to cos pi by 4n. The term that we have to do the summation to get the energy Ex will be equal to summation, the Ex3 will summation n equal to minus infinity to infinity modulus of cos squared pi by 4n. Okay. Modulus. So, you can write as cos pi by 4 modulus squared, or you can take the squared inside. So, this particular term cos squared pi by 4 can be written as pi by 4n, can be written trigonometrically. So, cos squared can be written as in the following manner: 1 by 2 into 1 plus cos of 2 theta pi by 2n. Okay, so this is the expression for cos squared. So, substitute for energy, this is summation n equal to minus infinity to infinity. I am going to have a half sitting inside and another term which is 1/2 cosine pi by 2n. Okay, cosine pi by 2n takes on the values 1, 0, minus 1, 0. So, if I keep adding it, eventually the plus 1s and minus 1s will cancel. So, this term does not contribute in the summation. what I will be left with is only this term, and remember I am adding from minus infinity to infinity, I am adding the value of 1/2. So, the energy of Ex3 will be infinity, which is not surprising. It is a periodic signal, it goes from minus infinity to infinity. If I calculate the energy of any periodic signal, it will go to infinity. On the other hand, if I calculate the power of this particular signal, P of x3, then what you find is that the cosine term does not contribute to the summation. This term will contribute, and it will contribute the factor equal to 1/2. You add 2k plus 1 terms, it will be 2k plus 1 times half divided by 2k plus 1, you will get the power to be equal. So, again being able to work with the trigonometric functions extremely helpful, and you should be comfortable working with that. Now, before we conclude this discussion, we also wanted to say that we brought in the notion of a bounded signal, and we also said that if the input is bounded and the output is bounded, then we can say that the LTI system is BIBO stable. So, input must be bounded. Input bounded meaning mod x of n must be less than or equal to some constant b of x, which is less than infinity. Can we show that y of n modulus is less than or equal to some constant for all values of n? So, check the following systems for BIBO stability. Okay, so BIBO stability, just a couple of examples, and then we move on to the new topics for today. BIBO stability, we are looking at the following system where y of n is equal to n times x of n, and it's a bounded input system. So, bounded input is given to us. So, mod x of n is less than or equal to bx less than infinity. This is given to us. Now, we want to know what is mod y of n. Mod y of n is modulus n modulus of x of n. This is equal to modulus of n less than or equal to, this is less than or equal to modulus of x of n is b of x. Now, there is a tendency to say, okay, this is the limit, but notice as limit n tends to infinity, modulus n b of x tends to infinity also. So, this particular sequence or this particular sequence will not be bounded, is not bounded. Okay. Input is bounded, output is not bounded. That implies the discrete time system is not BIBO stable. It is not BIBO stable. Again, you should be able to capture that. Okay, let us look at a second LTI system. Y of n equal to e power x of n. Now, you may say, well, you know what, you are taking exponents, things will become larger and larger, and therefore, this looks like it is going to be an unbounded system. Not quite. We are given that mod x of n is bounded, less than or equal to bx less than infinity. Okay. And how do you interpret this one? Mod x of n less than or equal to infinity, very important. So, this is saying that either x of n can be positive or negative. So, if it were positive, it would be x of n less than or equal to bx. Now, if x of n were negative, okay, then what we are saying is minus x of n is less than or equal to b of x, or x of n is greater than or equal to minus b of x. So, this is the other case, minus b of x. Okay. Now, if this is the two limits of x of n, what are the two limits of y of n? This is e power x of n, right, e power x of n. Okay. Now, this will be within the range e power bx less than or equal to e power minus bx. Okay. Now, the important thing to note is that there is an upper bound, right? There is an upper bound for this system. So, we can safely say that y of n is less than or equal to e power bx, which means y of n is bounded and the discrete time system is BIBO stable, All right. Okay. Now, one last one where I want you to look and think about it and see, because it's a combination of concepts. So therefore, I want you to take time to look at it carefully. Okay, this is example number 3. Y of n is given to us as summation k equal to 0 through infinity rho power k x of n minus k. This is the input output relationship. Okay. Now, very interesting. So, you can see that this is a convolution, right? This is a convolution. This is an LTI system, right? So, we are asked to look at but even if you do not recognize it as an LTI system, it's a convolution. It's a convolution of two sequences, h of n convolved with x of n. What is h of n? H of n is the one that is not time reversed. So, and the lower limit starts at k equal to 0. So, this is nothing but rho power n u of n. Now, please do this particular, take these two terms, write down the convolution and make sure that you are getting the expression that we got over there. Okay. Now, but that is not what we want. We want to know whether the system is BIBO stable. So, the expression that we have is mod x of n is less than or equal to b of x less than infinity. Okay. I want to know about mod y of n. Mod y of n is modulus k equal to 0 through infinity rho power k x of n minus k. This will be upper bounded by, take the modulus inside, summation k equal to 0 through infinity. This will be mod rho raised to the power k mod x of n minus k. We know that this term is always less than or equal to bx. So, then pull b of x outside the summation. This is less than or equal to b of x summation k equal to 0 through infinity mod rho raised to the power k. Okay, this is a geometric series which is b of x divided by 1 minus mod rho. Now, this convergence or this summation is true only if mod rho is less than 1, only if mod rho less than 1. That means it is a converging or a decaying exponential. So, mod rho less than 1 means it is a decaying exponential, and in that case you will get a upper bound for y which is given by bx divided by. So, by is equal to by, the upper bound for y will be bx divided by 1 minus mod rho. It is a constant and it is upper bound for y. On the other hand, if mod rho was greater than 1, greater than or equal to 1 also, then what we greater than 1? Then we get a growing exponential. It will eventually blow up, and therefore the output will not be bounded. Okay, we cannot get a closed form expression, we cannot get a upper bound, and therefore that is the limit of what we have.